Types of measurements. Today we're going to talk about the two primary types of measurements that we're going to be dealing with this year. Those are scalars and vectors. Scalars you should be familiar with. These are most of the measurements that you've done up to this point. If you remember back to 8th grade, we talked about this a little bit also. Scalars are measurements that are described completely by the number and the unit. Something like mass, something like time, something like intensity. These are measurements that all you need is the magnitude and the unit, and that's all the information that you need to completely describe that particular unit. And so those are the easiest units, I think, to deal with, but a lot of the measurements that we deal with in physics this year and that we're going to deal with are the second type, and that's what we call vectors. Vectors need not only the magnitude, not only the unit, but also the direction in which that particular measurement is acting. And so there are actually three pieces of information that are necessary to fully describe a vector. Some of the examples that we're going to come across of vectors this year are velocity, force, acceleration. All of our force fields are all vectors. And so you can see here we have our different measurements. And when we write vectors, so here we have force. And force we have 20 newtons. But that's not enough. We need a direction. 20 newtons up, 20 newtons down, or 20 newtons at some angle. Same thing here. We have 5 meters per second squared. Again, we need some direction. It could be as simple as drawing an arrow pointing in the direction, or it could be a much more specific angle measurement. And in general, when we're using angles for our measurements, if we imagine our XY axis, here's our X, here's our Y. The positive X axis is 0 degrees, and we go counterclockwise from there. So if we have something that's pointing along the positive Y, so straight up and down, that's going to be at a 90-degree angle. And if we have something that's pointing in the negative x direction, our angle there would be 180. And that's kind of the notation that we use just to keep things simple. But you can also even do something like north of west or south of west or east of north to indicate the direction that the angle is being measured from, as long as you're specific. The more specific, the better. And so when we have something like a scalar quantity where we just add the numbers together, so we have two 50-kilogram masses on a sled. What's the total mass on the sled? We add them together. It's 100 kilograms, pretty straightforward. Adding vectors is not that straightforward. It's not as easy. But once you get the hang of it, it's not too difficult either. So when our vectors are in the same direction, then we just add. So let's use force. It's going to be one of the more common units we're going to use this year. Let's assume also that this is a straight line. Okay, straight line. Okay, so let's call that a 10 Newton force. So you have 10 newtons of force, and we'll just give it something to act on. We'll say it acts on this box. So, and we'll even, all right, let's get a person. So that's a person. Yay! He's pushing in this direction with a 10 Newton force. Now along comes his buddy, slightly smaller buddy, to help push. He only pushes with a force of 5 newtons. Okay, now, the forces are in the same direction. They're vectors. The net force here is going to be 15 newtons. We have 10 newtons plus 5 newtons. So our net force here is going to be 15 newtons, but of course that's not complete. We have to have a direction, 15 newtons to the right. Okay, so that's if they're in the same direction. Pretty easy there. But let's give ourselves a little more room here. Let's say we have our buddy here. He's pushing in this direction with a force of 10 newtons. But along comes his arch nemesis. He does not want him to push the box. That's an angry face. And so he's going to push to the left with a force, but he's not quite as big, with a force of 8 newtons. So now they're in opposite directions. We're actually going to take the difference. So it's going to be 10 newtons minus 8 newtons. And so our net force is going to be 2 newtons in the direction of the larger force, which in this case is to the right. Okay, so we end up with a 2 Newton force to the right. Again, pretty straightforward. Think of it as positives and negatives. If the right direction to the right is positive, direction to the left is negative, it's still really an addition. It's just 10 plus negative 8, and we get a positive 10, which tells us is in the right facing direction, or to the right. So when they're in parallel, when they're in the same plane, either in the same direction or in opposite directions, again, we either add them or subtract them, and that gives us our net force. But that doesn't happen a lot. We're going to find in the real world that most vectors act at some angle to each other, and so then we have to start taking trig into account. And so this is where we get to use Pythagorean theorem. We get to use the little memory device that I think we probably all learned in math somewhere along the way. So, TOA, yeah, ringing a bell, I hope, which is sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and the tangent of an angle is the opposite side over the adjacent side. So down here, if we have our angle theta, then C would be the hypotenuse, B would be the opposite side, and A would be the adjacent side. And so if we have a side and an angle, then we can find pretty much anything else about this triangle. Here, again, we have Pythagorean theorem, c squared equals a squared plus b squared. So if we have the two legs of the triangle, we can find the hypotenuse. And then here's the rest of our relationships. And so if we have, let's just kind of give an example of this. So let's say we have a force acting 3 newtons and a force acting up of 6 newtons, and we want to find the net force. And so the net force acting on this object is going to be the hypotenuse of the triangle. And so that's going to be, we'll say Fn. And so our net force is going to equal the square root of 3 squared plus 6 squared. So we have the root of 9 plus 36. So we have the root of 45. And so we have 3 root which if we have our calculators, we should of course get that out into a decimal, but for right now you get the idea. And so that's how we add vectors that are acting at a 90-degree angle, and then we can use our trig to find the actual angle there. If those forces are not acting at a 90-degree angle, though, there's a couple different ways we can do this. The first and probably most straightforward is to use law of cosines. Law of cosine, L of C, which says that, hopefully we know this, c squared equals a squared plus b squared minus 2ab cosine theta. And this theta is the angle that's across from C. So here we're looking for c squared. We have a and we have b and we have this angle in between a and b. So a squared plus b squared minus 2ab, and then we're going to use this angle right there in the middle, plug it all in, and we're going to get our resultant vector, which is c. The other way we can approach this is what we call breaking it up into components. And so what we'll do is we're going to break this force B up into its x and y components. So if we know this magnitude B, and generally we have some way of finding this angle here, we're either given it or we can get it based on the measurements, we can find the y component here and we can find the x component here using our trig. So we know that sine theta is equal to opposite over adjacent, or opposite over hypotenuse rather. So that's y over, and we'll call this is going to be b, so y over b in this case. We're looking for y, so our y component is equal to sine theta b. And so then our x component is the adjacent side, so cosine theta equals x over b. And so our x side is equal to cosine theta times the hypotenuse, which in this case is b. So those are our two equations for that. So we have y equals sine theta b, x equals cosine theta b, and we're just using trig for that. And then once we have this x component, if you'll see that the x and the a are acting in the same direction, and then y is acting perpendicular, we essentially now have two sides that we're going to be finding the hypotenuse of that larger triangle. And so because a and x are in the same direction, we're going to add them together. We then have y. Now we can again then use Pythagorean theorem. In this case, it's going to be c squared equals a plus x squared plus y squared, and that gives us the hypotenuse. And so now we have the net of the vector, and this works whether we're talking about forces, acceleration, any measurement that is a vector, these methods are going to work for.